begin. There we go. Do you want to talk about equations of planes today? I know I do. Okay. Okay, we start today's discussion by asking, what criteria would we have to establish to even establish, to like find a plane, to like restrict ourselves to a plane in space? This is an analogous question to the one you might have had back in the day. When you're doing like lines in Algebra 1 or something like that, you might have thought, okay, well, if I have 2 points, that's enough to like determine the unique line that we're talking about, right? Or if I have the point, if I know the point and the slope, that's also a set of criteria that are good enough to establish a unique line. Or most recently, if you have the length of the normal and the angle of the normal, that's enough to establish a unique line in the plane. Yeah, you agree with me on that? So we have a couple different ways. So let's think broadly about this. Can you come up with as many different sets of criteria that force us into a single plane in space? What things would determine a plane? Just like 2 points determine a line, or a point in the slope determine a line. What determines a plane? Let's come up with a couple different options. 3 lines? Oh, 2 lines, provided that what? Okay, 2 parallel lines would be a good answer, I think. Yeah. Yeah. What else?
I want to say 2 perpendicular lines.
I think 2 perpendicular lines would be. I think the only requirement would be that they be what? 2 lines that intersect, right? Any intersecting pair of lines would have one common plane that they lie in. That'd be cool. I like that. Yeah. So we could ask that on the warm-up too. Find the plane that contains both of the lines that we had on the warm-up. That'd be cool. Yeah. Well, we're going to come up with equations for them today, for sure, and you'll like that. But right now we're just thinking visually. Like if I have like this, how do I nail this down in the room? Right now it's like lying all over floppy, right? But as soon as you say, hey, this line and this line need to be in the plane, I'm like, okay, well this line needs to be in the plane. Okay, now I'm here. You also need this line to be in the plane, right? You see, you've just arrested me. I forced the plane into that position now. So what else would force our hand in putting the plane in a particular place? 2 lines. That's a very creative first answer, I would say. What else? Most common answer I hear has not been said yet. Yeah. A cube?
Like a shape that you could like put this like here.
A 2-dimensional shape.
Or like a 3-dimensional shape.
I don't know how to provide that to you though. Like besides handing it to you. Right? Like 2 lines I could actually give you algebraically, right? I don't know how to give you a cube or something. I mean, I guess maybe we could come up with a way, yeah.
2 points?
2 points determine a plane. So if you have 2 points, I can draw a unique plane through those 2 points.
3.
Maybe not a unique plane. I think there are an infinite number of planes I could draw through any 2 points you give me. Am I right?
A point and a line then?
Oh, a point and a line, provided that the point and the line have what? What's not true about the point and the line? What has to be? Yeah, good. Right. Otherwise, it's just a line and we're wobbly again. But a line and a point not on the line would be okay. Yeah. 3 points, provided that they're not the same point. Well, that would be true. What else?
They're not all on the line.
They're not collinear, right? Because if they're all on the same line, then we have a wobbly plane again.
Think about
yeah.
it.
So 3 non-collinear points would be, I think, okay. I've established like a firm table on which to stand.
No,
Okay.
I think I get it.
You got something else?
No, but about the point thing. For example, a point in and of itself has no dimensions, but a line which has 2 points has 1 dimension.
Mm-hmm.
A plane which requires at least 3 points has 2 dimensions.
So if there was such a thing as like a 4-dimensional plane or something, maybe it would be established by like, yeah,
But like
by
if
4
you want to
points
make
or something.
if you want to make a 3-dimensional object, you're gonna need like 4 points to make. Wouldn't a triangular pyramid be the simplest one to make without taking a sphere?
I don't know exactly what you mean, but
Like with the minimum number of points you would need to make a 3-dimensional object would be 4.
that's true. I'm just trying to think how that relates to this. Yeah. I mean, it does relate to some extent. Yeah. Right. You should look up the word simplex tonight. Okay.
Simplex.
Simplex. Simplex. Simplex. It'll make you happy. Okay. Go. a vector in a third dimension. Okay, so a vector,
Yeah.
a three-dimensional vector of some kind.
So like X, Y, Z, C, X.
Okay, so I have a vector. What do you want me to do with it though?
Like have like, I don't know, I remember like when we learned about,
So it points, yeah, or so go ahead. So
yeah, so
what
then
do
we
you
like
want?
have, we have like one vector here, that one, and then it kind of creates a table.
Yeah, so what relationship should this vector have to the plane of that we're talking about? So you say I give you a vector.
Yeah.
I'd love to give you a vector. Here you go. So what would you like to do it?
Well, you have like two parts, and then we count, like maybe like the third
You
one.
just break my vector.
Sorry. You'd have like a third one, and then it would kind of fold up.
Let's say if you want a vector. Oh, so you want another vector too?
Yeah.
You want more vectors?
Yeah, and three vectors.
3 vectors? I can't afford to give you.
Yeah, so then it'd just be like this.
Oh, and then those vectors, okay. I liked where you were going at
If that
first, but I'm not
makes
sure.
sense.
Yeah, I don't know if that makes sense. I like the idea of using a vector because we're in this unit. Yeah, I don't know if you'll come up with this one or not by yourself, but there's a way to do it with a vector, and that's the way we're going to do it. It's not the way that you guys just decided. And that's the following. So use a vector and a point. So the vector I'd like to, so that is, let's make it really wobbly. Let's have it be balancing on one point in space, right? That obviously defines the plane only in a limited way. It has to go through that point, but it's very wobbly still. And then I say, oh wait, hold on. I need it to point in this direction. Go through this point and have it point in this direction, right? Then if it was wobbly before, it's not now, right? It needs to be pointing in that direction, yes? So you can see how that would do it maybe. You might not agree that that's the most elegant way to define it yet, but I think you have to agree that that will work, at least. And I have a nice 3D applet to show you in a second here that does what I just did in the arrow with my marker. Good, so in practice here, how I'll do it. And by the way, all the other answers are correct, and I think it'd be interesting to give you problems of all of those types, right? Like before you leave today, I'm going to give you one where you have 3 points and you'll determine the plane, so we'll do those. But this is the easiest way in on this problem, and I'll just recommend it to you, okay? So I'm going to, in practice, in a minute, like the very next slide where I give you a problem, I'm going to give you a normal vector to the plane, that is one that's perpendicular to the plane I want. So in practice, A, B, and C will be known. These are constants, right? I'll give you a normal vector. It'll be like whatever, 3, -1, 5. And I'll also give you a point that I desire to be in the plane, right? Whatever that might be, 3, 0, 20, something. And then my question is, what must be true about a generic point, another point, x, y, z, that we purport, we claim we want to be in the plane? Yeah. Yeah. Yeah, normal, orthogonal, whatever. We have all these words for it now. So yeah, we're going to give you a normal vector to the plane and a point in the plane. So all these letters, A, B, C, D, and F, are all known to you in the problem today. So I suggest that we build a vector from the known point to the unknown point, from D, E, F to X, Y, Z. Just go with me for a second on this. Can you imagine doing that? So you have, here's the plane of interest. You have a point, a known point, and here's our point. This one's fixed, right? It's given to us in the problem, so you don't need to move it. But X, Y, Z is another point that's in the plane, right? It could be anywhere you like. Doesn't matter. It's just a generic point X, Y, Z. And then we're going to build a vector from the point given to X, Y, Z. So what would that vector have as its component form? If it's from D, E, F to X, Y, Z. X, what'd you say? X minus D, Y minus E, Z minus F, right? Yeah. So that's the vector in the plane from our the given point to our point X, Y, Z. Now, let's say we have a vector that lies in the direction of the plane. Would you like to say what its relationship needs to be? This red vector to the other piece of information we haven't used yet, the blue vector, right? Like what if I give you the normal vector? What should be true about the red and the blue vector? If the red, if they're orthogonal. I mean, if the blue normal vector is supposed to be a vector that's orthogonal to the entire plane, then any vector at all that you build in the plane should be perpendicular to it, right? So that's equivalent to asking that what be true, that these two vectors have, if they're orthogonal, that they have what? two vectors are orthogonal. If and only if they're. Let me just take a quick one. Yeah. What'd you say? Yeah, the dot product is 0, right? So there it is, right? There's our, well, we need to clean this up a little bit, but this is actually our equation of the plane. I mean, we'll simplify this a little bit. But isn't this the requirement that we have? That with a vector we built, the generic vector we built from the point given to a generic point x, y, z, we require that it be perpendicular to ABC. That is, the dot product needs to be 0. So multiplying that out, I mean actually doing the dot product, do A times x minus d, and B times y minus e, and C times z minus f. And cleaning this up just a little bit, I'm just going to move things that don't have a variable in them to the right side. Right, so now I have, yeah, see I moved the AD, the BE, and the CF over from the left side to the right side. Just to emphasize that what we have right now is something times x plus something times y plus something times z equals just, you know, a constant, right? All of the in green here, this is all just one big constant, AD plus BE plus CF. So in general, if you ever come across an equation of this form, something times x plus something times y plus something times z equals something, guess what that is? It's a plane, right? In 3 dimensions, it's a plane. And maybe there's some structure here to look at that was like traceable back to the origins of how we got this. When you look at the equation, what do you see right away? The coefficients of x, y, and z are ABC, which is what? Yeah, it's the normal vector. ABC is the normal vector to the plane. So right away, if someone hands you the equation of the plane, you'll know right away that a normal vector to the plane is staring you in the face. What about the constant d? I chose to rename it capital D. It's really all of this garbage, though, isn't it? That collected into one name. Okay, so what is that? Also, if you wanted to like see where it came from, ABC is this guy, DEF is this guy. You recognize what that might be? AD plus BE plus CF. Okay, you know. Of what? Yeah, isn't this just in green the dot product of the normal vector with the position vector to the point? So in theory, maybe you could just like, boom, write this down. You wouldn't have to go through this. But I do kind of like going through this each time we do the problem, just because it reminds us of like where we came from. So there it is in a box again. Here's an applet that I'll click on, and we'll be able to drag it around. I have a freedom in this applet to choose a point and a normal vector, and we'll see that we'll see it happen. Right? We'll see that we can generate different planes. You ready? It's so fun. Here we go. So moving the red point around just repositions the plane, right? But if we move the green vector, it's kind of like honing in on a satellite or something, like trying to get a signal, right? If we move the green vector around, it reorients the plane, right? So you can see that the red point given and the green normal vector do in fact determine a plane, right? In fact, I have a nice diagram of this down here too. This is what we did a second ago with the 2W mold, right? I said here's a point, and here's an arbitrary XYZ point in the plane. You see that how we build the vector from the red given point to our arbitrary point in yellow, the XYZ point. All these teal vectors that we will be creating, all of them are orthogonal to the green normal vector, right? No matter what vector you make in the direction of the plane. Yeah. The plane does not have a limit. It goes on forever, but we can't do that. So the window is only a certain size and all that. Actually, I think if I use the keyboard, I might be able to zoom in and out and stuff. Maybe, I don't know. Anyway, hopefully that's a good visual in terms of describing what I did with the marker and notebook and all that. Yeah.
But if the plane has no limit, then couldn't the point be like anywhere in like the realm of like where it could be, which is everywhere?
Say that again.
If the plane has like no limit because it doesn't have like an edge, right? It doesn't have like a defined edge, then couldn't the point, the like generic point be anywhere on the
plane is not everywhere.
Well, I mean, like where? You know, like
What is everywhere?
that's the
Visa,
question for
I
philosophy.
think, isn't it? Isn't Visa everywhere? Oh, sorry. Or is it MasterCard? I can't remember. Yeah. Isn't it Visa everywhere you want to be? Is it what it is? No, the point, it's infinite, but it's not every point. You know, I think you're suggesting that every point in all of three-dimensional space is on the plane. Is that what you're suggesting?
I mean, I think so.
I think that's not correct. There are an infinite number of points on the plane. That's correct. But it's not true to say that, like, is the point 2, 3, 7 on your plane? No, not necessarily, right?
Wait, so a plane is two-dimensional.
Correct.
Yes.
But it lives in 3 dimensions, right? Right?
Well, if it's two-dimensional, then it can't be three-dimensional because if it's
In fact,
it has three dimensions, right?
no.
Technically, it is an undefined geometrical figure.
It is
and
actually.
It cannot exist in reality, but in a conceptual three-dimensional space, it can exist because geometry.
Yeah, the only way we can conceive of two-dimensional objects is if we're embedded in 3 dimensions. Right?
But for something to be everywhere, it would have to fill every dimension.
This got just really deep really quick. Let's move on. But I would love to talk about this later with you. Yeah. The idea of surfaces embedded in 3 dimensions is an idea that definitely excites me. So we'll like talk sometime about it later. You can. Yeah.
I'm still kind of confused how only one vector is needed to like find a plane.
Yeah. So again, you like fix a point in space. Can you imagine a plane going through that point? There are an infinite number of choices for that plane, right, in terms of orientation. But then I said, no, hold up. If your plane is like a giant mirror, I need you to point it to the sun. Suddenly I forced your hand. You need to like rotate it exactly in
So
that
like
direction.
vector is more to like orient it.
Yeah.
I need something
Yeah, the
sharp and a
point,
piece of
the
paper.
point puts it in space. The vector orients it at that point, right?
So is it
Here, I can just apply an example.
like a plane? So
Are you guys doing this, by the way? Ready, go.
For example, see this piece of paper? You can rotate it infinite number of ways at
You
one
want
point,
to
right?
Yeah.
Oh, okay.
But steer it through something. Boom. Now it can't move. This would have been a better example had it been better with resistant gravity.
I like it.
You get what I'm trying to say, right?
Do this problem. Ready, go. You're already done? Wonderful. Wonderful. I didn't give you everything that you need to know in order to do that problem there, but you need to figure out. I would derive it the same way we did a second ago, right? Do a point, x, y, z, create a vector, and then do that product of it equal to 0. Multiply that. Alright, do we get it? Alright, so you could just do this every time, right? Like I said, x minus whatever. So we'll do it up here together. X minus 1, y minus 5, z minus plus 2, dotted with 1, negative 2, 4, needs to be 0. And so there's our equation. We just need to clean it up a little bit. That's all, right? So we x minus 1 minus 2y plus 10 plus 4z plus 8. How are we doing on that? Equals 0. Check my arithmetic along the way. So we get what? X minus 2y plus 4z equals 18 minus 1 is 17. So let's move that over to the other side, I guess, if we want it in this form. I guess there's nothing special about this form per se, but I think we did it, right? And again, staring you in the face is, when you're done, hopefully, the normal vector is sitting here. You don't have to write this work down if you understand where this stuff comes from. You can just like write the equation down, that's fine. So you'll just have the normal vector here always. And then the negative 17, like someone pointed out earlier, is, and you can get it from just collecting garbage from up here. But it's also, it turns out to just be the dot product of position vector to the point and the normal vector. If you check it, you can see 1, negative 10, and negative 8. Oh yeah. How do you like it? You're doing planes, guys. Isn't it fun? Okay. The way people usually graph it is by graphing, if by hand, I think is what you mean, is by graphing something called the trace of the plane, finding the intercept of the plane with the x-axis, and the y and the z-axis, and then drawing like a corner of it, right? And then you could imagine that it actually extends infinitely in all directions. So you could find, right? So for this, like where does this hit the x-axis? The x-axis, this sets the x-axis at negative 17. This is not the picture of this, obviously. This hits the y-axis when those are both 0, right? So at 17 halves, right? So you can see how you might find those 3 points, and then you can visualize it pretty quickly. Or you could get some software to graph it for you too. We can maybe do some of that. All right, this is the promised question that some of you suggested at the beginning. What about 3 points, right? Can we do it with 3 points? And the answer should be yeah, right? So let's see if we can do it. But we kind of need a way in on this. I mean, we need, what do we need? A point and a vector normal to the plane. All right, well, we have a point. In fact, we have plenty of them, right? You could pick any one of those to be your point in the plane, right? So we've got a point for sure. So we're on a mission right now to find a vector normal to the plane, which we don't seem to have yet. And then we'll just have the previous problem. If we can get those 2 things, we'll be like, yes.
I know how to.
Where is your sticks? Okay, go ahead.
If we take vector QR and we do a dot product that should come out to 0, we can go backwards to try to find the orthogonal vector.
Okay. Now the only issue with that is, by the way, I like the idea of forming some vectors here. So QR, for example, is, let me do this here with you. That negative 7, 5, negative 1. So I like the idea of forming some vectors. There's QR, for example. Right? I think I did that right. Okay. And I like what you're saying. You're trying to think of another vector that's like orthogonal to this. The only issue is there are an infinite number of vectors that are orthogonal to a given vector, aren't they? Yeah. Maybe we need another vector. Let's make, what vector would you like to make, Leo? What other vector? Huh? QS. I love it. Okay. All right, let's make another vector. 3 to 2, so that's what, negative 1. 2. Is that negative 5? Check me on those, okay? So now, it's not good enough to just be like, hey, we need a vector orthogonal to this one, because there are an infinite number of them. But it is interesting to have the requirement that we need a vector that's orthogonal to both of them. That is interesting. That does fix me. doesn't it? That fixes us in a certain direction. There is probably only one vector or two or an infinite number that all point along the same line or something. Yeah. So how do we find a vector that is going to be orthogonal to both of these vectors?
Why couldn't you just do QR and then just use S as
Well, QR is not a normal vector to the plane. It's a vector that's in the direction of the plane, right? So now we need to get out of the plane, right? So we have two vectors. Anytime you form any vectors you like here, you'll get vectors in the direction of the plane, right? None of them help us get out of the plane yet. Do we have a way of getting a vector that is orthogonal to both of these vectors? Come on, somebody say it. Eric's going to come in strong. Here it comes. You ready? He's going to drop a bomb. The cross product! All right, you knew it was coming. All right, here we go. So, Eric, where would we even be today without you? I don't even know. And the crowd goes wild. Okay. Check my arithmetic. You do it too. Okay. Alright, so it's at negative 25 plus 2. Negative 23. I. Check me on these, please. Please. Check me, check me. One way you can check it is just to take the dot product again with each of these and see if it's 0, right? I hope you understand the gravity of this situation. How important what we've just done is, right? So we now have a normal vector, don't we? Our normal vector is negative 23, negative 34, or anything coterminal to it. Excuse me, or anything, any scalar multiple of that will do. If you want to switch them all to positives, that's fine too. Negative 36. Let me check it here. Negative. It's 35 minus 1.
Negative 1 times negative 1 is minus 1. So negative 35 minus 1 is negative 36.
Wait, hold up. So we do 35, positive 35.
Oh, it's negative 1.
So 35, positive 35, minus 1, which is 34. And then in the middle, we always make it the opposite, right?
I understand the gravity. It is a
I think that's right. I think it's
0,
right.
negative 1.
Can someone back me up out there, please? Give me some love. All
I
right.
understand the gravity. It's a vector in the direction of 0, 0, negative 1.
All right. So there's a normal vector. Which point would you like to use? You can use any of them. Q. How about? All right. So together we have a point and a normal vector. Go. Find the equation of the plane again. Right. We're ready to do that now. Okay. I'll wait. The numbers are a little messy, sorry. Yeah. It doesn't because, I mean, you cross them the other way and come back to populous. Yeah. Yeah, it'll just be 23, 34 now. Yeah, but it'll still be perpendicular. Yeah. So what do we get here? Negative 23x minus 34y minus 9z equals something. I don't know what. Negative 23 times 3. Oh man, I don't know. Negative 69 minus 18. Negative 87. All right, yeah. So I said the equation of the plane is, and do you agree? Is this. Yeah? Okay, and by the way, feel free to multiply all those by negative 1. Don't you have that irresistible urge to do that? I do, I know. I don't know about you. Feel free to do that. If this comes out and has an even multiple, all of them are evenly multiple by even multiple of 6 or something, feel free to divide 3 by 6. Do whatever you like to do to clean it up would be fine. The homework tonight is obviously do this worksheet front and back. That is your homework 8. Okay, it should say that on the homework sheet. Tomorrow we have an IQ problem. Did you do that? Okay, good. I'm glad you did that.
Yeah. Direction, 0, 0, negative. Bottom. Do you like the direction in which this conversation is heading?
Shameful puns.
It's the direction of gravity because it's downward. Got it? That's gravity.
I think that's good. We should, huh? You want the review sheet? I want to get that out. Bye, guys. Isn't that amazing? Life-changing? So cool. Well, guys, have a great day, you guys. See you tomorrow. Oh, I was hoping someone would come at it. I don't know the answer off the top of my head, but you told me how you did it.
Basic cross product thing.
Yeah, now that we talked about this, right? So, no, it's good. So what you do is you use the...
I just like find the two being and I just get the cross product with them. And then the routing
Okay, so where's the equation of the line?
it will be 2 minus 1 to plus 2.
Come over here for your fabulous prize. Are you ready?
Oh boy.
It's a pack of Skittles. There you go. You're welcome.
Nine.
What's up, Lauren?
I came for the joke of the day.
No, you didn't. You came for this illusion. Are you ready? Please. You may want to be sitting down for this. What shape do you see as the cross section of each of these? What shape does it have as a cross section? Yeah, like a diamond or a square.
Oh my god.
Right? Isn't that trippy?
What? Wait.
You could argue about it. You put it in the middle. Argue about it.
Is this? Oh, I get it.
It is appropriate. like a heart, and from the other perspective a square or something like that. Great. You can actually get out a printout. You can get. We actually do have some down here. This one Simon printed on his one that they use for robotics. I think that you must be confusing that with something else. So here's what I think that they do have. You can do, and that's to draw something in three dimensions on the web, just like what we were tracing down in the lines, right? That makes sense. Virtually, and then you can have it printed out.
I've done it. You write with it. It looks like that. How? Yes. I promise. Like you just mark on the page. No, you don't like write on paper. It's like in the air.
It just puts. You just put it down.
Yeah.
Yeah.
It's not like a pen. It's like, but it's like in a pen shape.
So is it connected with a lot of filament? You have filament coming through
Yeah.
it? Yeah. And
Like
it pumps out
it's like a
filament.
hot glue gun, but like a pen.
Right. So it is basically like a hot glue gun. I mean, we have, in some sense, we've had that kind of 3D printer since for a long time. Like the glue gun, like a big hot glue gun, is basically a 3D printer, right? As it cools, you can like create whatever you want with that. Or frosting, right? Oh, I'm sorry. Oh, I love this. I love that. Yeah, isn't that great? A limerick, a riddle, and a poem walk into a bar.
I'm in a jam.
But no joke.
I'm in a joke. I'm talking. Jam it.
Does that make sense? Any new tricks? Any new tricks yet?
That was scary. I thought it was gonna hit me in the face. I could like feel the wind, but I was in the front row. Like the circus fire. Okay. Do you have to ride the bus? I guess I'm not anymore because I'm too late. I was just
Oh, cool. Yeah, do a little bit of cross product, a little bit of. See you guys. A little bit of angular momentum, torque. You know, some of that. But, yeah. So the direction of torque is perpendicular to so the time when I think about that, you maybe haven't thought about this. So the direction of the angular momentum for that is
When you
perpendicular
throw it up,
to it.
it's perpendicular to the string.
Yeah, so this, if it's rotating this way, then the direction of its angular momentum vector is like this, in this direction. Or if it's rotating this way, it's this way, following the right hand rule.
Oh, we didn't really do that. There was not